So the last talk of the day is by Emine Yildirim, and it would be on cluster structures. So please.
Thank you very much, Claire, for introduction. And I'd like to thank the organizers for such a great conference and the program at Isaac Newton Institute. Also, thank you everyone for coming to my talk. I'd like to make a small announcement before my talk. So there will be seminar series at Isaac Newton Institute starting September 28. So they will held Tuesdays from 4 to 5 UK time. And the format will be like this conference. We will have speakers at Isaac Newton, and then people who want to join, they can join in the Zoom. So it will be a hybrid seminar series. And our first speaker is Emily Gunawan on September 28. So, and then we will send the announcement very soon with the links and all the information. Okay. Yes, I also put my slides in the chat, and I like to put two references in the chat. So the first one is by Fomin-Pylyavskyy about tensor diagrams Chris just talked about. So you may want to see concrete definitions of these objects, because in the short talk, we didn't have really time to go over them. I will not as well. So, and then the other paper I'm going to send in the chat is by Jensen-King-Su about the categorification of Grassmannian cluster algebras. So these are the two main references for my talk. And this will give you a clue that what I'm going to talk about. So let's start. So so this is a joint work, ongoing work with Ian Lay from Australian National University. Yes, it's still an ongoing work. It's in early stage. So this project started last fall during the program New Trends in Representation Theory at HIM Bonn. So what we are trying to do is, so Chris talked about these nice objects, and there are beautiful cluster structures coming from this combinatorial setting. So Chris talked about the different surface, but for me, I will always consider these nice tensor diagrams. Chris called them tensor diagrams. I will call them webs, but webs are just planar tensor diagrams. So these are the objects I'm talking will be the same as the Chris. Yeah, so what I was, yeah, okay. So the first thing we have is Fomin-Pylyavskyy cluster structures in the ring of SLV invariants. Yeah, so yeah, this is what I wanted to say. I'm always considering the disk, but the things, as you will hear, they will be also a similar version of the Chris talk. Yeah, so there is this nice combinatorics happening in the combinatoric of tensor diagrams and webs, which are related to the ring of SLV invariants. And on the other side, we have a very nice categorification of Grassmannian cluster algebra in the sense of Jensen-King-Su. Then it's natural to ask, is there any relation between these two different settings? Because the cluster structure on the homogeneous coordinate ring of Grassmannian is just a special case of the cluster structures in the ring of SLV invariants of n tuple of vectors in a k-dimensional vector space. So yeah, so then it is natural to ask the Fomin-Pylyavskyy cluster structure coincide with the cluster structures coming from the setting of Jensen-King-Su. So actually, even in their paper, tensor diagrams and cluster algebras, Fomin-Pylyavskyy states that thus the web basis, which is the main object that carries the cluster structure. Thus, web basis coincides with the dual semi-canonical basis of Lutzig. So then it is very natural to think about the Jensen-King-Su categorification and try to relate if there is any connection. So that's the motivation. Of course, the classical invariant theory studies more general rings. So in the paper by Fomin-Pylyavskyy, they look at this ring. It's not just Grassmannians. So their setting is more general. And in the paper, they work on three-dimensional vector space. And then in that case, they show the cluster structure in this ring. And yeah, in the paper, they conjecture that every such ring carries a cluster algebra structure. So they proved it in the case of three-dimensional vector space, because thanks to the beautiful bases they have, web bases, but they conjecture that every such a ring should carry such a cluster algebra structure. So it's quite nice, and having such a general conjecture motivates the question in the Grassmannians. Yeah, so this is what I just said. Yeah, the web basis is introduced by Kuperberg, and it's a basis for the ring of invariants for the three-dimensional vector space. And so the webs are the elements, and these are exactly as Christoph, they are nothing but planar tensor diagrams. Yeah, so a web is a planar bipartite graph plus some properties. The explicit definition is in the paper of Fomin-Pylyavskyy. Yeah, there's no point of going in details, but I also like to show you some pictures. So basically, they are used to pictorially represent certain elements in the invariant theory. So here I'm showing you some webs, tensor diagrams, and so they are embedded in the disk. So in the Fomin-Pylyavskyy, they also looked at, of course, general surfaces, but the paper I referenced, they only have the combinatorics. That paper includes combinatorics embedded in the disk. But as you've seen in Chris' talk, these beautiful objects and these bipartite graphs extends to different surfaces. Here's one thing, like I have two different set of webs. Here I only have black vertices on the boundary. And this means I'm only working with some power of the vector space, but a priority, since Fomin-Pylyavskyy work with this ring, the V dual VA. So a priority, we may have the points representing the vectors from the dual basis, dual space. So yeah, in their setting, they have this type of collection of webs. But I will be also interested in the webs in this looking, namely the boundary vertices are all black, because these will relate to the Grassmannian cluster algebras. But I just want to mention that this combinatorics extends, so that these are elements in the ring of invariant, SLV invariant. So let's talk about one explicit example. So Grassmannian 3-6. The cluster algebra, in this case, it's type D4, so it's a finite type. And the invariants in this case are functions of 3 by 6 matrix. right? We have Grassmannian tree-6, so we have the minor of this matrix. They are the invariant, basically the determinant, and how a tensor diagram or a web represents an invariant, an element. So there's a very nice recipe in the paper I sent, but for instance, I just want to give one explicit example. Here we see a web, which is a tensor diagram, and it has 6 vertices because we are working in Grassmannian tree 6, and we have 3 edges. We only have this tripod because this is the simplest case that I can show you. And what this means is we are choosing 3 vectors here. So if I draw this diagram like this, connecting 1, 3, 4, that means I want to compute the invariant, this invariant, which has this vector, and this vector. So that the determinant of this will give you the invariant. And I can actually compute this invariant by just looking at this picture and doing some combinatorics. So there is a recipe by coloring these edges and choosing particular elements at each step and then adding up, and then it will explicitly give me this determinant. So these tensor diagrams, these webs, with a combinatorial recipe, they produce elements in the invariant ring. And it's really just choosing certain coloring on these, and with respect to those coloring, choosing these, the product of these variables. And yeah, so in this example, we should have 22 cluster variables if you have already looked at this cluster algebra. And then in this case, 20 of them will come from this web, because we will have a choice. We can choose 3 vertices from the 6, and each of them will give me a cluster variable. And then there are 2 non-Fluker cluster variables in this case, which are explicitly these 2 pictures. Okay. Yeah, so this is just a quick note. An invariant associated to a non-elliptic web is called a web invariant. So this is not really complicated. It is a little bit technical, but we just don't want multiple edges and a certain configuration in the web, because as Chris mentioned, there are skein relations. You can reduce webs and get somehow the reduced version of them, the most beautiful version of them. And then when you write the invariant, we call it web invariant. And as Chris mentioned, so Fomin-Pylyavskyy conjectures all cluster monomials are web invariants. So it is very nice. I don't know if it happens to Chris, but as we discuss in this project, these are all conjecture, but we treat them as, okay, these are true, and we try to find things. It's sometimes we even forget that these are all conjectures, because I also do believe in that using these webs, we get these web invariants, and they correspond to cluster monomials. And I believe the Fomin-Pylyavskyy conjecturally describe which one of them should be cluster variable even. So these are all conjectural procedure, but they work pretty perfectly. So we sometimes forget that they are conjecture. We assume them and somehow work with them. Yeah, so this is the story in the Fomin-Pylyavskyy side. And then, yeah, so there's this nice, beautiful story, and it has nice cluster structures. Of course, on the other side, we show cluster structures in the context of representation theory. And what we are trying to do, we are trying to see if these two different cluster structure talk to each other. And in this case, we like to look at this categorification, in the Grassmannians. And I want to talk about the algebra that they are using in this paper. It's easy to describe. So what we have, so I have 6 vertices drawn in this skewer, but you can imagine I have n vertices in a circular fashion, and I put arrows between them in this fashion. So I have one way going this way and then this way. So usually the arrows outside are labeled with x, x1, x2, x3. So I just write xy, but this is x1, x2, x3. You can think of them like this. And then the arrow inside, it's y1, y2, y3, and so on. So we want to consider the path algebra over the skewer. And then we want to have some relations. So the relations are at each vertex we have, we should have xy is equal to yx. So as I said, I suppress the i's, but this is for each vertex. So we will have n relations coming from here and n other relation coming from this. This k is fixed, and it is with respect to which Grassmannian you want to work with. And when you fix k, you will have n other relations. And this is basically saying if, for instance, k is equal to 3, if I go 3 steps this way, it should be equal to going 3 steps this way with y's. Okay, and then, yeah, we take this algebra and they look at the completion of this algebra, and they use the module category of this algebra to categorify the cluster combinatorics in the Grassmannian. So this is the reference I put in the chat. Of course, this is an infinite dimensional. The modules are infinite dimensional. It's quite technical to work with this algebra, but they have a beautiful description of modules in terms of ranks, and somehow the building blocks of blocks in this algebra are the rank 1 modules, and they understand them very well because they correspond to Pulukar coordinates in the homogeneous coordinate ring of Grassmannian. So the rank 1 modules, which are in correspondence with the Pulukar coordinates, are well understood. And all the other module have, every other module has a filtration using rank 1 modules. Yeah, so that we have this big collection of modules, but they can be understood using this strategy. So we have rank 1 modules, rank 2 modules, rank 3 modules. So these modules have filtration, and there is a very nice way to look at these modules. So I think I have time. I can show you a little picture. So yeah, for instance, in the Pulukar coordinates, so to determine combinatorially the Pulukar coordinates, for instance, what we do, we want to choose the K subset in N. And you want a similar combinatorial data in this other site as well. And then when you look at the modules, you want this like a simple combinatorial data to determine the module you want to work with. For Pulukar coordinates, so you want a similar combinatorial data to identify the rank 1 modules. And so here I drew rank 1 modules, and so you can imagine our skewer here. I opened it up. So this is a circular skewer, but let's think that I opened it up, and then I'm writing the module over this diagrammatically like this. So so these vertexes, you can think of it, it's opened. And so so how do we determine these rank 1 modules combinatorially? For instance, if I again go back to the same example, Grassmannian tree 6, so I want to see the module corresponding to 1, 3, 5. So what we do, we draw the lattice paths in this lattice diagram, and 1, 3, 5 tells you the down steps. So here I have 1, here I have 3, here I have 5. So 1, 3, 5. So this is 2, this is 3, 4, 5, and 6. So these 3 down steps determine somehow my rank 1 module combinatorially. And then for all the other ranks, so Chris said in the tensor diagrams, what you do, you took these 2 tensor diagrams and then you stack them on the top of each other to find somehow the higher rank tensor diagrams. And here, the similar story, you have these rank 1 modules, and then you stack them in a certain way, and then you get higher rank modules. Okay, so this is very hand-wavy description of these modules, but since the Grassmannian cluster algebras, they're really combinatorial, even this module structure, they're quite complicated, but we can somehow describe them combinatorially in a very nice way. Okay, so, and there has been some studies on, rank 1 modules are really well understood, no question there, but there are recent papers on the rank 2 modules by many authors. Like I wrote one paper, I forgot to write the name of the paper, but by these authors, Bauer, Bogdanik, Elsener, and Lee. And then they do study the rank 2 modules in their paper. And they have a theorem. So they say that, so this looks complicated. We don't really have to understand what is this formula, but there is a number. And then they say that there is at most this number of rigid rank 2 indecomposable in the nice module category of this algebra that I described. I think Eleanor also talked about this. So this is the same, the Cohen-Macaulay modules over this path algebra, but I think Eleanor used the capital F. But so this is quite nice because there is this number, you can compute it in the examples and see if it's true, and it's true, and it gives this counting on the rigid rank 2 indecomposable modules. It's quite nice, and then they actually conjecture that this should be exactly the number of rigid indecomposable rank 2 modules, and we do believe in that. This is, I think, true. And with Ian Lee, in the ongoing work, we found a one-to-one correspondence between rank 2 rigid indecomposable and certain functions in the Grassmannian, which can be pictured by webs. I mean, in the paper, like Ian used this notation for the functions, but basically these are just webs. They're another way of labeling or naming the webs. So I want to show an example. So for the rank 2 webs will look like basically these 3 webs. This is in this case, of course, I have Grassmannian 510, but what I mean is for the rank 2 modules, what do I have? I have this tripod in the middle, and then they will have these branches attached to the white vertices. So I ignore the disk, but you can think that they are all embedded in the disk. So in the rank 2 case, it's quite simple. You have a tripod in the middle, and then the leaves attached to these white vertices. So for instance, these webs I draw here, they correspond to cluster variables. And then I somehow illustrated the corresponding rank 2 webs. So as I said, we can label the rank 2 webs, the rank 1 webs with the lattice pad only looking at the down steps, and the rank 2 ones are just stacking them to each other, right? So I have these type of pictures for the rank 2 webs. And yeah, so they're quite combinatorial as well. And then we were able to find a recipe to go from a web to the rank 2 modules. So this is combinatorial. One thing we want to do, of course, we believe that we understand the rank 2 webs and which are the cluster variables. And then you stack them on the top of each other, you get cluster monomials. You can resolve them using skein relation and so on. So that we know the web invariants correspond to these webs. And then in the Jensen-King-Su setting, there is also a cluster character formula. So we can put these modules into a formula and find out what are the cluster variable corresponding to these modules. It's still a difficult question to check if they coincide, namely the cluster variables I get from these web invariants are the same as the cluster variable coming from the corresponding module. But we hope to also investigate this further. And actually, like the whole point was to see, okay, we have this cluster variable and we want to say this is the corresponding web and this is the corresponding module to the same cluster. And so this correspondence is actually more deep. So this is all what I want to say. Thank you very much.
And thank you very much. Are there some questions? Maybe first in the room.
Can you hear me?
Yes.
I just wanted to clarify the last thing you were saying. You know, presumably the tripods or K relevant vertices, and the things corresponding to look coordinates, you presumably do know that the function is the cluster character of the model. Is that right?
I couldn't really hear it very well, but if Claire, you...
No, I also had trouble to can you repeat, please?
Know that the CC map works out for Fluker coordinates.
Yes.
Yeah, I think I haven't computed it, but I'm sure. I think we did some actually way back when I was a PhD student. We did some calculation, and I remember that I think that for Plukers, I'm sorry, I'm vague, but because we were trying to write a computer program to check higher, like even rank 3 modules corresponding to rank 3 webs, somehow these more complicated webs. And then even that was the case. We computed one rank 3. So because of that, I believe, I don't remember the computations, but I believe they should coincide.
Well, the point was that if you know that, and you know that the projection you have commutes to the mutation, then you know it's for all reachable objects by the multiplication, because there is a constant.
So did I again have hard time to hear, but did I understand? So you start with the Kluckers and then you mutate and you get all the others?
Well, that's what I'm, yeah, I'm sorry, I don't know where to point my voice so that you can hear us. The, yeah, as long as your bijection between webs and modules respects mutations, then if you check that the functions agree on Kuperberg coordinates, then they agree on all reachable things.
Mm-hmm. Yeah, this is one thing I think we should work on to like if it respect the mutation and because I mean, okay, we are trying to see these mutation dynamic using rank 1 modules, and so using rank 1 modules we get these certain rank 2 ones, but there were some difficulties on the way because I don't think on the module side I still understand how the mutation goes with the rank 1 modules, like how if I iterate it. I think in the web combinatorics side, Ian knows how to mutate this rank 2 functions in the Grassmannian and what you get. He knows all of them, but I should work on the representation side more, like start with a seed of rank 1 modules mutated and get all rank 2, rank 3. I'm still trying to understand how this works.
Right.
Okay, any other question?
I can ask a question.
Sure.
Sure.
Can you show your slides again?
Yeah. Sorry.
One thing is you have this like notation. It's a little surprising to me. So like on the 3,133, there's like an extra leg that's going to the top.
Yeah, it doesn't, I mean, it doesn't have
Couldn't there
to
also
go
be
to
a left
here.
such leg, or the notation just isn't what I'm guessing? Yeah.
So this, yeah, so this, we should have one leg, like, but it can, it doesn't have to connect here. It can connect to here too.
Yes, but also couldn't there be kind of, I don't know what the notation is, but couldn't there be like lots of legs, not just sort of like.
Yeah. I mean, so
Yeah.
here I have 3, 3, 3, right? So
Yes.
1, 2, 3, 1, 2, 3, 1, 2, 3, and then
Yes.
1 is this one.
But you could have like 3,1 and 3,1 in another leg or something. Because the notation you wrote is just A, B, C, D.
Yeah, this is exactly A, B, C, D, that's it. No,
That's strange.
in the rank 2 case, yes, this is what it is.
Mm-hmm. And also, can you explain a little bit how the numbers like 4, 2, 2, 4 are reflected in the module?
Yeah, so for instance, this is 4, 2, 2. This is the core, A, B, C, right? It's actually quite easy. A is the number here attached to this white vertex, 4, right?
Mm-hmm.
And then I have 2 and then 2.
But in the module.
Yeah.
Yes.
In the module.
Yes.
Yeah, that's our procedure, which is not trivial.
You can't just say it. Yeah. Okay.
I think I can, but I should tell it to you separately maybe, because it is cumbersome, a little bit cumbersome.
Sounds good. Thank you.
Yeah.
Okay, any other questions? No, so it doesn't seem to be the case. So thank you very much, Emine, again.
Thank you.
And maybe we should thank also all the speakers of the afternoon. So thank you, everyone.